Now we will do an application on the Taylor series expansion. Well, about this integral, right? Now, although we have done so many methods to do an integral, none of those methods will help you to compute this integral. Although this function looks like a very simple function, surprisingly this integral cannot be evaluated with those methods that we learned before. You can just give it a try, and of course let me know if you were able to figure out a method to compute this integral, to evaluate. And this is how we should do the integral by using the binomial expansion. Sorry, not the binomial expansion, but the Maclaurin series. Now what we can do is, we already know that the Maclaurin series of e to the power x is this one, and you have to remember this equation, right? This formula. And then by substituting negative x squared as this term, we can say that, we can come up with the corresponding Maclaurin series for this specific term, which is the function inside the integral. So finding the integral of this one is the same as finding the integral of this one. Remember, I said in the very beginning when I introduced you to the power series, I said integrating the terms of the powers, integrating this whole big power series is the same as integrating the terms and adding them up, right? So here what we do is integrating the terms separately and adding the whole series together, right? So when you do the integral, you just have to integrate the terms one by one, or in fact we need the integral of this general term, right? So when you do that, you will get an arbitrary constant, of course, and then it's like for each and every term you will get an arbitrary constant, but putting all those arbitrary constants together, we can just write a single arbitrary constant, and this one will be equal to x, and this one will be equal to x cubed over 3 times 1 factorial, and this one will be x to the power 7. I think there is a change of okay, the mistake is here. Well, the third term will be 4, right? And the next term will be 6 over 6 factorial with the negative term. So after this one you have this, right? Okay, so anyway, now accordingly the integral of this one will be 5 divided by 5 times 2 factorial negative x to the power 7 divided by 7 times 3 factorial, and likewise you can obtain the integrals. So eventually we will end up with a power series expansion of this format: 2n plus 1 2n plus 1 over n factorial, which is basically the power series, the integral of this general term. Okay, and you have to have a arbitrary constant since you are doing the indefinite integrals. And how about now see, we have at first we had a simple function which we need to find the integral, but surprisingly we were unable to do it with the methods that we have done so far. Hence we went for the power series expansion, in fact the Maclaurin series, and we integrated the Maclaurin series term by term. And for power series, of course, you can integrating the whole power series is the same as integrating the term by term and adding them up. So that's what we did here, and we can see that this thing will change into this new series. So what we have done is we have written down the integral of this function as a power series. So what if we need to calculate a definite integral out of this one? For example, what if we need to evaluate something like this? That means we need the two upper and lower limits in here. Or in other words, we need to evaluate the upper and lower limits in here. That means we need the upper and lower limits evaluated for each and every term in here. Then now, since we have the 0 as the lower limit, when you substitute the 0, all these terms will vanish. And also when you are doing the definite integrals, this arbitrary constant will also vanish. So the only effect will come from this upper limit. Then when we substitute the upper limit, we get terms like this, right? 10 minus 1 over 42 plus 1 over 216, and likewise, right? And then you can see, now we cannot find the exact value of this series, right? Because this series is an alternating series with infinite number of terms, so we cannot add an infinite number of terms. That means we cannot find the exact answer for this integral. But what we can do is we can do an approximation. So if we have the problem like this, what we can, like, to evaluate the integral correct within an error of this much, we can use the alternating series approximation theorem to evaluate this one up to this given particular error margin. And so for that, if we evaluate this term, the next term, the term after this 1 divided by 2, 116, you can see that it is less than or equal to 0.001. It's actually strictly less than 0.001. So from the alternating series approximation theorem, it says that the addition of the terms up to this point will give you the suitable accuracy. So in fact, when you add these terms, you will have 0.7475, and that means we can safely say that the value of our integrals 0 to 1 ex squared dx will be equal to 0.7475, and it has an accuracy of 0.001, right? So it is accurate up to this position, right? Okay, so this is how we make use of this Maclaurin series theory or the Taylor series theory to evaluate integrals, right? So now see, this is a very simple looking function, and taking the derivatives is not difficult at all. But when it comes to integration, you cannot just integrate whatever the function they give you, right? It's difficult. So we have to go for different techniques like this in order to come up with the suitable value for this integral. In fact, a suitable value for this definite integral. So what we have done is we have approximated an integral. Now here it should be 2. We have approximated an integral by the knowledge we had in Maclaurin series. And I will conclude this week's session in the next video with another application of the Maclaurin series.